Let's take a look at this capacitor circuit. This circuit has one EMF device, a battery, with a voltage V across it, and it has 5 capacitors arranged, some in series and perhaps some in parallel. What we want to do is find the charge transferred from the battery to the capacitors in this circuit. What do we know about the relationship between charge on a capacitor and the voltage? What we know is a relationship that charge Q is equal to the capacitance times the voltage across it. What does that circuit model look like if we have a capacitor with a capacitance of C and a voltage across the plates of the capacitor of V? Then the charge on the plates of the capacitor will be Q. Well, what we have here is 5 capacitors. This EMF device has to charge all 5 of the capacitors. So if we could find the charge on C1, we'll call it Q1. The charge on Q2, we'll call it Q2. The charge on C3, we'll call Q3, Q4, and Q5. Then the total charge transferred from the battery to the capacitors would be equal to the sum of all 5 charges, or from I is equal to 1 to n of Qi. Or perhaps there's an easier way to do this. Since if we could determine the equivalent capacitance that this EMF device sees, that equivalent capacitance seen by the voltage source would have on its plates the total charge. So to do this, the problem becomes a problem of combining capacitors. Combining capacitors, we have to recognize when capacitors are in series and when capacitors are in parallel. Capacitors in series are connected only at one of the 2 terminals. As an example, these 2 capacitors would be in series. We can recognize here that C2 and C3 are in series. None of the capacitors right now are individually in parallel. We see that C4 is in parallel with a series combination of C2 and C3. When capacitors are in series, they're only connected by one of the 2 terminals. And when they are in series, they have the same charge on the plates. So series, same charge on the plates. So when we combine capacitors in series, our relationship is that the equivalent capacitance is equal to 1 over C1 plus 1 over C2, or it's equal to C1 times C2 divided by C1 plus C2. We can redraw our circuit and we can rename the equivalent capacitance C2 and C3 as just C23. And now we can recognize that we have 2 capacitors in parallel. C23 is in parallel with C4. When 2 capacitors are in parallel, both the terminals of the capacitor is connected. So we see here that the top plate of C23 is connected to the top plate of C4, and the bottom plate of C23 is connected to the bottom plate of C4. When 2 capacitors are in parallel, they share the same voltage across their plates. Parallel, same voltage across their plates. To combine capacitors in parallel, the equivalent capacitance is just equal to C23 plus C4. It's the sum of the two capacitances. So let's take a look at that combination. When we combine C23 and C4, we come up with the capacitance C234 as a notation. Our C subscript 234 is now in series. Since they are in series, we know they will have the same charge on their plates. C234 Q5, such that Q5 will equal Q234. They're in series. We can find their equivalent capacitance by combining them. To combine the two capacitors in series, 1 over capacitance C234 plus 1 over capacitance C5, the reciprocal of that is the equivalent capacitance. So if we do a little combination, we get an equivalent capacitance for C2345, and we recognize in this equivalent circuit we have two capacitors that are in parallel, and they're in parallel with our battery. The definition of things being in parallel means they share the same equal potential surfaces. If they share the same equal potential surfaces, that means they have the same voltage across them. So we can find the charge on capacitor 2345, we'll call it Q2345, and the charge on capacitor 1, and our total charge will be equal to the sum of the charges on both the plates. 2, 3, 4, 5. So we can now use our equation. So using our equation, Q is equal to CV. We know Q is going to be Q total will equal C1V plus C2, 3, 4, 5 times V. So let's put some numbers into play here. Let's say each of the capacitors, C1 is equal to C2 is equal to C3 equal to C4, which is equal to C5. Let's let them equal 10 microfarads. And let's let our voltage source supply 5 volts. Our total charge then will be equal to C1, which is 10 microfarads, 10 microfarads, yes, times our 5 volts, plus we've got to find this equivalent capacitance. This equivalent capacitance then would be 10 microfarads cubed, which would be what? 10 cubed plus 10 cubed plus 10 cubed divided by 1, 2, 3, 4, 5. So we get 3 10 cubed in the bottom, 5 times 10 squared in the denominator, and we end up with 3/5, 30 divided by 5, 30 over 5, or 6 microfarads. So we'll plug that in, 6 microfarads times 5 volts, and we end up with 16 microfarads times our 5 volts, or 16 times 5 is 80 microcoulombs. And for these numbers, that would be our result. Well, what if we want to find just the charge Q2, or perhaps the voltage across capacitor C2? Watch the next video to find out that.